Hello and welcome once again on a session on a special theory of relativity. We have discussed Galilean transformations in the last session, and we have seen how these Galilean transformations and Newton's mechanics go hand in hand. We have also seen that from Maxwell's equations in electrodynamics we get one constant C, which is equal to 1 upon square root of mu naught epsilon naught. This constant is identified as velocity of propagation of plane wave in vacuum. However, according to Galilean transformation, such velocity cannot be same for observers in different inertial frames, and according to Galilean transformations, there is no limit on the velocity of the object as well. Based on this discussion, we considered three possibilities. First possibility, the Galilean transformation exists for mechanics but not for electrodynamics. For electrodynamics, there is a preferred inertial frame which is called as ether frame. But when attempts were made to find out such ether frame, those attempts failed, and therefore this first possibility was discarded. Second possibility, relativity principle exists both for mechanics and electrodynamics, but laws of electrodynamics given by Maxwell are not correct. But experimental evidences show that the laws of electrodynamics are correct and there is no deviation from the Maxwell's equations. So second possibility was also discarded, and then we arrived ultimately at the third possibility, which says relativity principle exists both for mechanics and electrodynamics, but the laws given by Newton are not correct. We also have seen that Newtonian mechanics could explain the motion of the objects which are moving with comparatively lower speeds, but when it comes to the speeds comparable to speed of light, the predictions given by Newton's theory could not match with the experimental results, and therefore there was a need to develop a new theory which will be applicable to all speeds of particles. Einstein in 1905 developed a special theory of relativity for inertial frames of reference. So in this lecture we will be discussing this postulates of special theory of relativity, and as Galilean transformations are no longer applicable now, the new transformations we will try to obtain, which are called as Lorentz transformations, which will be obtained with the help of the postulates of special theory of relativity. In 1905, Einstein, when he was 26-year-old, developed a special theory of relativity for inertial frames of reference. And to develop this theory, he did two assumptions which are called as postulates of special theory of relativity. The first postulate states that the laws of physics are same in all inertial frames. No preferred inertial system exists. This postulate is called as the principle of relativity. So if one law of physics is applicable in one frame, then the same law of physics must be applicable in other inertial frame as well. The second postulate states that the speed of light in free space has the same value c in all inertial frames. This postulate is called as the principle of constancy of the speed of light. After around 10 years, he developed one more theory which is called as general theory of relativity, and this general theory of relativity is applicable to non-inertial frames or accelerated frames, and it is found that a special theory of relativity is a special case of this general theory of relativity. Now let us see how Lorentz transformations are obtained by using the postulates of special theory of relativity. To obtain Lorentz transformation, let us consider again two frames of references, frame S having the origin O and frame S prime having the origin O prime. Let some event occurs at point P, and when space-time coordinates are measured from each frame of reference, the observer in frame S specify the space-time coordinates as x, y, z, t, and the observer in frame S prime specify the coordinates as x prime, y prime, z prime, t prime. Let the new transformations be x prime is equal to ax plus bt, y prime, z prime will not change because the frame s prime is moving only in x direction. So y prime will be equal to y, z prime will be equal to z, t prime let it be equal to cx plus dt. Here this a, b, c and d are the constants whose values we will try to find. Once we get the values of a, b, c and d, we can write the Lorentz transformations. So let us consider an event x, y, z at time t in frame S. Let x is equal to vt, y is equal to 0 and z is equal to 0. So the point P is somewhere here in frame S, and x prime is equal to 0, y prime is equal to 0, z prime is equal to 0. So the point P is at the origin of the frame S prime. From equation 1 we can write x prime, which is equal to 0, is equal to a vt, because x is equal to vt plus bt. We'll just take out t common. So av plus b t equal to 0. Therefore av plus b can be written to be equal to 0, and we can get the third equation, which is the relation between constant b and constant a, which can be written as b equal to minus av. So this is equation number 3. So this is equation number 3, b is equal to minus av. So now we are left with only 3 constants. In order to get the values of these 3 constants, let us consider a light wave spreading from a common point O and O prime when they coincide. So as the frame S and frame S prime are moving, there will be some time instance when O and O prime will coincide. So at that time instance, let us consider a wave, light wave spreading in all directions. Now we will consider 3 events. When the light wave reaches point P, this is event number 1. When the light wave reaches point Q, that is event number 2. And when the light wave reaches point R, that is the event number 3. For each of these events, we will try to get one equation, and with these 3 equations and 3 unknowns, we can find the values of the constants. So let us consider the event 1, when the light wave reaches point P. So when light wave reaches point P, it travels the distance equal to ct, where c is velocity of light. In time t, it will travel the distance ct. So distance traveled along x direction is equal to ct. So x is equal to ct in frame S. Y is equal to 0 and z is equal to 0 for point P. Now we will use Einstein postulate of constancy of the velocity of light. So according to Einstein postulate, speed of light is constant in all inertial frames. Therefore an observer in frame S prime will also measure the velocity of light at c only, and therefore x prime can also be written as ct prime. T prime is the time measured in frame S prime. So from equation number 1, x prime is also written as ax plus bt, and b is equal to minus av. And using this equation 1 and equation 3, we can also write x prime to be equal to a into x minus a into vt. Here a is taken common, and we can write it as a into bracket x minus vt. We have already written x is equal to ct, so this x is just replaced by ct, and t also can be taken common here. So we can write x prime to be equal to at into bracket c minus v in frame S prime. From equation number 2, t prime is equal to cx plus dt, x is equal to ct. So we can take t common from here, and we can write cc plus d into t. that is equal to t prime. From here x prime equal to c t prime, we can write c to be equal to x prime upon t prime. This is speed of light actually. C is equal to speed of light, which is equal to x prime upon t prime. X prime we have already found at into c minus v, and t prime is cc plus d into t. Capital C is the constant and small c is speed of light. So just cancelling t from numerator and denominator, we will get c to be equal to a into c minus v upon cc plus d. So this is actually a small c. So we can write this equation as cc square plus dc, that is equal to a into bracket c minus v. So this we got for event number 1, we got one equation that we are calling as equation number 4. So now let us consider event 2, when the light waves reaches point Q. So when the light wave reaches point Q, again it has traveled distance ct in negative x direction, and therefore x is equal to minus ct in frame S, y is again equal to 0, z is again equal to 0. In the same way as we did in the earlier slide, because c is constant in all inertial frame according to Einstein postulate, in frame S prime also the speed of light will be c only, and we can write x prime to be equal to minus ct prime. And the same way as we did in earlier slide, x prime is equal to ax plus bt and b is equal to minus av, we can write this x prime to be equal to a into bracket x minus vt. X is again replaced by minus ct here, as we are writing x is equal to minus ct, and then we can take t common and we can get the relation for x prime as minus at into bracket c plus v. Again by using equation number 2, t prime is equal to cx plus dt, x is minus ct, so we can take t common and we can write it as minus cc plus d into t. Now again c is equal to minus x prime upon t prime. From here we can write it as c is equal to minus x prime upon t prime. X prime value we have already found, so it is at c plus v upon minus cc plus dt. Again tt will get cancelled and we can get the relation for c as a c plus v upon minus cc plus d. From this we can write equation number 5. One more equation we are getting here, minus cc square plus dc equal to ac plus v. So let us call this as equation number 5, which is obtained for event number 2 when the light wave reaches point Q. Same procedure we will follow to get the one more equation when the light wave reaches point R for event 3. So for event 3, when the light wave reaches point R, see in which direction the light wave is traveling now? It is traveling in the y direction. So displacement along x direction is 0. So x is equal to 0. Y is equal to ct now and z is equal to 0 in frame S at some time t. Again here we will use equation 1, x prime equal to ax plus bt and b is equal to minus av to write x prime to be equal to a into bracket x minus vt. Here x is equal to 0 from here, and therefore we can write for event 3, we can write x prime to be equal to minus avt. Now y prime will be equal to ct, same as y, and z prime will be equal to 0. We can write y prime to be equal to ct because velocity of light is constant in all frames, all inertial frames. So at time t prime in S prime, we can write y prime to be equal to ct. From equation number 2, t prime is equal to cx plus dt. So t prime equal to cx plus dt. Here x is equal to 0 for event 3, and therefore we can write t prime to be equal to dt. So t prime equal to dt for event 3. Now the frame S prime is moving with velocity v with relative to frame S, and therefore the distance of point R from point O prime can be written as square root of x prime square plus y prime square plus z prime square, and this distance will be equal to c into t prime. So x prime we have already found, minus avt, so x prime square will be equal to a square v square t square. Y prime is equal to ct, so y prime square is equal to c square t square, and z prime equal to 0, so it is 0. So we can write c square t prime square equal to a square v square plus c square t square is taken common here, that is equal to c square d square t square. This we are writing from here actually, t prime equal to dt. So t prime square is equal to d square t square. So we got one more equation here. This t square t square can be cancelled, and we can write one more equation, a square v square plus c square equal to c square d square. So this equation we are calling as equation number 6. So from event 1, event 2 and event 3, we got 3 equations, c square plus dc equal to a c minus v, that is equation number 4, minus c square plus dc equal to a into bracket c plus v, that is equation number 5, a square v square plus c square equal to c square d square, that is equation number 6. So these are the 3 equations now with 3 unknowns, a, c and d. So we can get the values of 3 constants a, c and d by solving these 3 equations. Once we get the value of a, the value of b can be easily found by using equation number 3. Now to find the values of constants a, c and d, let us first add equation 4 and 5. So when you add equation 4 and 5, c square will get cancelled, av will get cancelled with av, and therefore we can write dc plus dc, that is 2dc, that is equal to ac plus ac, that is 2ac. Here also we can cancel 2c from both left and right side, and we will get d is equal to a or a is equal to d. Let us call this as equation number 7. Let us put this equation number 7 in equation number 6 now. So we will replace d by a here. So we can write a square v square plus c square is equal to c square d square, d is replaced by a here. Just rearrange the terms, a square c square minus v square is equal to c square, and therefore we can write a square to be equal to c square upon c square minus v square. This can be written as 1 upon 1 minus v square by c square. So taking square root on both sides, we can write a to be equal to 1 upon square root of 1 minus v square by c square. And from equation number 7, a is also equal to d. So we can write a equal to d equal to 1 upon square root of 1 minus v square by c square. So this becomes our equation number 8. So we have got the values of constants a and d. Now from equation number 3, b is equal to minus av, and therefore value of b can also be obtained, which is equal to minus v upon square root of 1 minus v square by c square. So this becomes our equation number 9. So we got the values of constants a, b and d. Now the constant remaining is what? C. So let us try to get the value of constant c. So we got a equal to d equal to 1 upon square root of 1 minus v square by c square, b is equal to minus av from equation 3, so it can be written as minus v upon square root of 1 minus v square by c square. Now in order to get the value of constant c, we will just put a equal to d in equation number 4. So when you put A equal to D, D equal to A actually, we can write it as CC square plus AC. D is equal to A, so AC equal to AC minus AV. So AC minus AV. From this we can write C to be equal to minus A V upon C square, that is equal to minus V by C square upon square root of 1 minus V square by C square. So this is our equation number 10, which gives the value of constant C. So now we are available with values of all constants A, B, C and D. So let us put these values of constants in equation number 1 and equation number 2, and we can write the Lorentz transformations. So in order to get the Lorentz transformations, we'll just put the values of constants A, B, C and D in equation number 1 and equation number 2. So x prime is equal to Ax plus Bt. So A is equal to 1 upon square root of 1 minus V square by C square into x. So it is x upon square root of 1 minus V square by C square minus Bt. B is equal to minus V by square root of 1 minus V square by C square. So in this B into T, so it becomes Vt upon square root of 1 minus V square by C square. We can write it as x minus Vt upon square root of 1 minus V square by C square. Now y prime is equal to y and z prime equal to z, because the frames are moving with velocity, relative velocity v along x direction. So y coordinate and z coordinate will not change. T prime is equal to Cx plus dt. So C value is what? Minus V by C square upon square root of 1 minus V square by C square. So when you multiply C by x, you will get minus Vx by C square upon square root of 1 minus V square by C square plus dt. So d is 1 by square root of 1 minus V square by C square into t. So that is t upon square root of 1 minus V square by C square. This denominator is same, so we can write it as t minus Vx by C square upon square root of 1 minus V square by C square. So these are the Lorentz transformations. X prime is equal to x minus Vt upon square root of 1 minus V square by C square, y prime equal to y, z prime equal to z, t prime equal to t minus Vx by C square upon square root of 1 minus V square by C square. This is how we have got the Lorentz transformations. So now we got the Lorentz transformations. X prime equal to x minus Vt upon square root of 1 minus V square by C square, and t prime equal to t minus Vx by C square upon square root of 1 minus V square by C square. In these Lorentz transformations, if we put V much less than C, then let us see what is the result. The result is interesting. If we put V much less than C, then V square upon C square can be neglected in comparison with 1, and what will be left with x prime equal to x minus Vt, which is nothing but Galilean transformation. Let us see in case of t what happens in t prime. If V is very much less than C, again here also the denominator will become approximately equal to 1, and in the numerator also Vx upon C square will be negligible, and this will reduce this Lorentz transformation to t prime equal to t, which is nothing but Galilean transformation. This means what? This means Galilean transformations are not totally wrong, but Galilean transformations will be applicable only for the velocities which are much less than the velocity of light. When velocity of the object becomes comparable to velocity of light, then Galilean transformation will not be applicable, and we will have to go for Lorentz transformation. So for lower speeds, Galilean transformations are still okay, but when we go for the speeds comparable to velocity of light, that is when v is very close to c, then Galilean transformations are not applicable and we will have to consider Lorentz transformations. These Lorentz transformations give rise to two important phenomena, time dilation and length contraction. So let us discuss these two phenomena, time dilation and length contraction, one by one. Before going to time dilation and length contraction, let us first discuss Lorentz velocity transformations. Lorentz transformations we have written as x prime equal to x minus vt upon square root of 1 minus v square by c square, and t prime equal to t minus vx by c square upon square root of 1 minus v square by c square. By differentiating, we can write dx prime to be equal to dx minus v dt upon square root of 1 minus v square by c square. V is the velocity with which the frame s prime is moving, which is constant. So dt prime can be written as dt minus v by c square dx upon square root of 1 minus v square by c square. The velocity ux prime can be written as dx prime by dt prime. So if you divide this dx prime by dt prime, we can get dx minus v dt upon dt minus v by c square dx. Let us divide numerator and denominator by dt. So we will get dx by dt minus v dt by dt, dt will get cancelled, so v will remain here, upon dt by dt, that is 1 minus v by c square dx by dt. Dx by dt is nothing but ux minus v upon 1 minus dx by dt is again ux v by c square. So this is the velocity transformation. We can also write ux to be equal to ux prime plus v upon 1 plus ux prime v upon c square. So this is the Lorentz velocity transformation. Based on Lorentz velocity transformation, let us try to show that addition of any velocity to velocity of light is not greater than velocity of light. So this can be proved by using Lorentz velocity transformation. So we have Lorentz velocity transformation is given by ux equal to ux prime plus v upon 1 plus ux prime v by c square. So here let ux prime is equal to c and v is equal to x into c, where x can be any number. So we are trying to add any velocity x into c to velocity c here. So let us add this velocity v, which is equal to xc, to ux prime, which is equal to c. So ux is equal to c plus xc. So ux prime is replaced by c, v is replaced by xc, upon 1 plus ux prime is replaced by c and v is replaced by xc upon c square. So this can be written as by taking c common, we can write it as c into bracket 1 plus x upon 1 plus c into c is c square into x. C square will get cancelled and will be left with 1 plus x in the denominator. So this 1 plus x will get cancelled and ux will be equal to c. So what we did here, we tried to add some velocity x into c, any random velocity x into c to velocity of light, that is c, and the result is what? C. So when we try to add any velocity v to c, the result is c only according to Lorentz transformation. So according to Lorentz transformation, when we add any velocity to velocity of light, the result will be velocity of light. The addition will not be greater than velocity of light, but it will be equal to velocity of light only. So we are at the end of session number 3 on special theory of relativity. In this session we obtained Lorentz transformations, and we have seen that these Lorentz transformations reduce to the Galilean transformations for lower speeds. We also proved with the help of Lorentz transformation that addition of velocity to any velocity of light is not greater than velocity of light. In the next session, we will get introduced to the phenomenon called time dilation, length contraction, and then we will study the mass energy equivalence. So we will try to get that relation, famous relation, E is equal to mc square. I hope you must have enjoyed this session. If you like this session, then please subscribe to the channel. If you have any doubts, if you have any queries, you can write in the comment section or you can mail me on mail ID. So thank you once again.